In a round-robin chess tournament, the number of games required varies with the number of players competing. The table shows the number of players in games. Use finite differences to generate a quadratic function model for g of x, the number of games of chess in the round-robin tournament, in terms of the number of players participating. Then, compare the domain and range of the function model to the domain and range of the dataset. Okay, let's go ahead and first find these finite differences. So looking at our x values first, then we see that delta x, well, 6 minus 5 is just 1, 5 minus 4 is 1, and so on. So delta x is 1, and then g of x, we see 15 minus 10 here is 5, 10 minus 6 is 4, 6 minus 3 is 3, and 3 minus 1 is 2. And that's not constant, which is what we would expect since it's quadratic, so let's go ahead and find the second difference. So 5 minus 4 is 1, 4 minus 3 is 1, and 3 minus 2 is 1. So our second difference is 1, so we can go ahead and use our rules. We know that 2a will equal the second difference, which in our case is 1. And remember that our generic quadratic function is ax squared plus bx plus c. And so this will be our a value. So we can divide by 2 to solve for a. So we have a equals 1/2. And then the next rule we know is a plus b will equal the first difference between x equals 0 and x equals 1. And so here it's a little bit tricky since we aren't given those x values, and so we have to work backwards to find them. So that's pretty easy to do since we know what the delta g of x is going to be. And so, we know that next it's going to change by 1 again, our first difference. So 2 will go down by 1, and then we know then that g of x will go down by 1. So 1 minus 1 is 0. And so that's at x equals 1. And then doing that again, we know that the second difference will be 1. So 1 will go down by 1 and become 0. And then we know that g of x will then go down by 0. And so that just means that 0 minus 0 is 0, and so it won't change. And so then our first difference between x equals 0 and x equals 1 is going to be 0. So then if a is 1/2, then we can subtract 1/2 on each side, and we get b equals negative 1/2. And lastly, c is just our y-intercept. And so at x equals 0, then g of x is 0. And so that's going to be our c value. And so then we can go ahead and fill in a, b, and c. So g of x will equal 1/2 x squared minus 1/2 x plus 0. Let's go ahead and convert this into decimal form. That's actually what our answer is going to be in. And so 1/2 is the same thing as 5/10. And so we can rewrite this as g of x equals 5/10 x squared minus 5/10 x plus 0. We really don't need to put a 0 on the end, but that will just help us understand better our domain and range. And so for the domain and range, then with our function model, a quadratic, then we know that the domain is going to be all real numbers because we can plug in any number for x. And so we could write that as the set of x's such that x is in the real number set. And then for the range, this is a little bit different because we first need to consider what's our a value. Well, our a value is positive. That means that our parabola is going up. And then we also need to consider then, well, that means it has a minimum. And so what's going to be that lowest y value? And that value would be c. So our function will never go below 0. And so we can write that as the set of g of x such that g of x is greater than or equal to 0. And then our data set you see is very specific. And so it actually does fall within our domain and range in the function model, but it's a specific subset. And so first for the value of x's, the set of x's, such that, well, here they're all whole numbers. So we can say x is in the whole number set, and it's just a range of numbers within that set. And so we go ahead and write x is within the whole numbers, and then we know it's between 2 and 6. So we can write 2 is less than or equal to x is less than or equal to 6. And then g of x, those are also whole numbers, but they're a specific set, not in order. And so we can just go ahead and write these specifically out. So the set of g of x, and then such that g of x is equal to those specific numbers. And so again, our domain and range for a function model have infinitely more values than our data set, but the data set is just a specific subset of that. And so let's go ahead and summarize our answer. G of x equals 5/10 x squared minus 5/10 x plus 0. Then we have our domains and ranges for our function model and our data set. Since g of x is a quadratic function whose leading coefficient is positive, its domain is all real numbers and its range contains all real numbers greater than or equal to 0. The data set, however, has a domain and range that are specific subsets of whole numbers. Infinitely more data points are contained in the domain and range of the function model, g of x, than in the finite data set.